All right, let's look at how concavity and the trapezoid method are related in terms of approximating the area under a curve with the trapezoid approximation method. As you probably already know, that the area under the curve is equivalent to the integral of that function. So if we took the area under the curve from this point to this point, it would be the same if we had some formula for this function. I just drew it randomly. I don't know what it would be. But if we integrated the formula for that function from this point to this point, took the integral from this point to this point, it would be the same as taking the area under the graph from this point to this point. So sometimes if you have a function graphically and you have no idea what its formula is, we might do a trapezoid approximation to kind of determine its area without having to integrate this really complicated formula. All right, to start, we have our curve, and we're going to start by just taking different x values, and they can be as sparse or as dense as you want, but the more x's we have here, the more choices we pick, the more accurate our approximation is going to be. So let me pick a few. Here I've labeled some various x's from x0, x1, x2, x3, x4, x5, x6, x7. And now we're going to want to find out what our function's f of x value is at that x. So we'll dot up here, and this point here is f of x0 all the way up to here. Here's f of x1. And I'm just going to dot each of these x's up to find its respective f of x value. Such as up here, we're going to dot it all the way up. This point here is going to be f of x4. All right, so here I've kind of dotted all the x values up to their y values. And then this is the part where we make a triangle, where we have this be base 1 of a triangle, not a triangle, a trapezoid. Have this, so this right here is f of x1. This is f of x0. And we're going to connect the trapezoid like this. And then our height is going to be this x1 minus x0. And we can call this delta x1, this interval delta x2, this interval delta x3. Let me label that just for clarity. You can see we are going to make a bunch of trapezoids by having one base of, and do you see how each, except for the endpoints, each x value will be used in two trapezoids, this one and this one. And this f of x2 is going to be used as a base for this trapezoid, and then it's also going to be used for a base for this trapezoid. So we have our trapezoids, and let me just remind you of the area of a trapezoid. Which is base 1 plus base 2 over 2 times the height. That's the average of the two bases times the height. And so for each trapezoid, for example, let's take this guy. His area is going to be base 1 plus base 2 over 2. So it's going to be f of x0 plus f of x1 over 2 times the height, which is delta x1. F of x0 plus f of x1 over 2 times x1. And then we're going to keep adding up all of these trapezoids. So then plus, and then this guy, which is going to be f of x1 plus f of x2 over 2 times delta x2. And that's going to get that guy. Plus, and then we're going to get another sum. And another sum. We're going to get the trapezoid, and then we're going to do all the trapezoids that we have made. For example, one of them later will be f of x4 plus f of x5 over 2 times delta x5. That's going to be this guy. This is the first base up to f of x4, the second base f of x5, and then our height trapezoid is going to be that distance here, this delta x5. So now as you can see, we have trapezoids which approximate this whole guy, and I'll even color in those trapezoids. So it's a little hard to see, but we have our original curve. I'm just going to fix it a little bit. And the parts in red are the parts that are part of a trapezoid but are above the actual curve. So those are going to be over approximations. And the stuff here that's in white, I just kind of erased it. But if you can see, I have a trapezoid here, and the area approximation only goes up to here. But the actual curve is going up to here. So this white part here isn't going to be included in our trapezoid approximation. So this trapezoid is going to be an under approximation. Same with here. We have this white part with this white part. But over here, our curve goes like this, and from here to here, we had this trapezoid. So it's going to be taking in all of this, even though the area under the curve is only this much. It's hard to see, but it's only like this much. We have this whole chunk outside the curve. Same here, the area under the curve is only from the black line below in green, but our trapezoid is accounting for this red space too, which is above our curve. So that's going to be an over approximation. Now let's try to figure out why that happens and if that has to do with whether a function is increasing, decreasing, concave up, concave down, and yeah. So let's look first at concave up. Just to remind us, there are a couple ways of remembering what concave up means versus its other guy, concave down, which is here. But we don't want to look at that guy. Concave up, you can think about it as the arrows point up, and you can also think about it as the slope is steeper with a higher y value and lower when there's a lower y value. So up here, obviously, the values of f of x are higher and the values of f of x of lower. Up here, let's, maybe this is 10. Maybe this is -2. Well, the tangent lines, if we draw tangent lines to this curve, the very best I can. It's eventually going to get, well, that was a terrible tangent line, but here. So as you can see, the lower the y value, this is flat at the very bottom, and as y increases, these slopes are gonna get steeper. Like here, it's flat. Here, sorry, I'm gonna try to move my finger. Here's completely flat. Here's a little bit more. Here's a little bit more. Here's a little bit more. This is getting steeper. Same. It's getting steeper. So concave up, the slope is steeper upwards. It's higher, the higher up you are, the steeper you are. And it looks like a valley. Concave down, the arrows are pointing down. It looks like a mountain. And the lower you are, the steeper the curve is, and the higher altitude you get, the flatter it gets. So you can think about it as concave down gets steeper as it goes down, flatter as it goes higher. The opposite, concave up, was flatter at the bottom, but as the altitude increased, it got steeper. Okay, so now let's look at how the trapezoid approximation is affected by concave up or concave down, increasing, decreasing. Okay, so obviously here we have a concave, say in your head. Did you say up? Good job. Concave up. And let's say we take here an X, here an X, here an X, here an X. And let's draw our trapezoids for what's under the curve. Let's actually do it here. As you can see, when you connect the trapezoid, your trapezoid is going to over-approximate. And it doesn't matter whether it's increasing or decreasing, because here we have concave up. Decreasing, it over-approximated. Increasing, it over-approximated too. And for here, I'll do it in blue. Let's take here, 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 here. Maybe like here. Our trapezoids are underestimating because we have this white part that's not approximated by our trapezoid. And one last one is if the function is neither concave up or concave down. Here we have linear functions. We have an increasing linear, decreasing linear, and constant linear. You can probably already tell what's going to happen, but our trapezoid approximations are going to be exact because there isn't a curve. Because when we have a curve, that's what's causing the over-under approximation. This was the concave up, where it over-approximated. Concave down, where it under-approximated. But if we don't have the curviness, just the linear function, the trapezoid approximation is going to be exact. Here, it's not really a trapezoid, it's a rectangle. All rectangles are trapezoids. Just like in the trapezoid approximation, it's base 1. It's the average of the two bases. Well, here the two bases are the same. So let's say this is 5, this was 5. 5 plus 5 over 2 is still 5. So that's accurate as well. It doesn't matter. The increasing, decreasing, constant doesn't affect over or under approximation for the trapezoid method. It's the concave up versus concave down. All right, that's all.